Here we are, Janae. Welcome to the next episode of the Becoming Young podcast, where we're going to explore the cutting edge of health, longevity, and the pursuit of living your best life. How you doing?
I'm doing so great, and I am so excited for today because we have the one and only, our special guest today is Dr. Aubrey de Grey.
Welcome.
Great to be here. Great to be here.
Fantastic. So for all of our audience, Dr. de Grey is a biomedical gerontologist. He is an author and the visionary thinker who has dedicated his career to unraveling the mysteries of aging and advocating for strategies to combat age-related decline. He is the guy. He is the one who has really brought forward the idea of age-related decline with sorry here, let's cut that for a minute. Thank you. Dr. de Grey is the guy who has brought us damage accumulation and how that works with our age-related decline. I just want to hop right into it, Aubrey. 20 years ago, you made a switch from computer science to studying aging. Can you talk to us a little bit about how you made that leap and why you're so passionate about this?
Well, actually, it's 30 years ago now. It was in the mid-90s.
Well, you look so young still. It must be working.
You're very kind. Well, basically, it all happened because I discovered that biologists were not working on aging, to speak of, which was something that had never occurred to me until then. I had always known, it just as a kind of obvious fact of life, that aging is by far the world's most important problem, the thing that causes the most suffering, the thing that kills the most people, and so on. And so it had just never occurred to me that anyone would not think that. And so I'd never, discussed it with anybody. And I decided as a young child that I wanted to work in some area that would make a big difference to the world. And that was what led me initially to go into artificial intelligence research, because when I was about 15, I started programming, found I was pretty good at it. So I thought, I'll use that. But then, I was doing perfectly well in that area. In the mid-90s, or the early 90s, I met and married a biologist. And she was a lot older than me, already a full professor at UC San Diego. And through her, I, learned a lot of biology over the dinner table by accident. But in addition, after a couple of years, I began to realize that we were never talking about aging. And I started asking questions and discovered that she just wasn't interested in aging. She decided it was not her problem. And this was the same for all the other biologists that I was meeting. So I was completely blown away by this. But, eventually I came to terms with it and decided, well, I've got to switch fields, really, because I seem to be fairly good at working on hard problems. My AI research had gone pretty well. So I thought maybe I've got a chance of making a contribution.
I love
fantastic.
that. Now, one of the questions I have within this background is it seems that you approach this in a really unique manner because you have the computer science background, and a lot of the medical industry doesn't have that type of background. Can you speak a little bit to how this kind of gives your research and your perspective on this a unique edge?
Sure. Well, I wouldn't say it's unique anymore. Certainly when I came in, one of the reasons I felt I might be able to make a contribution was because I was coming from a different discipline and had maybe a different way of thinking about the problem. And certainly there's a quite distinguished litany of examples of that in science. So the most conspicuous one is that the whole of molecular biology was invented back in the 1950s by a bunch of physicists. I thought that might make a difference, and sure enough, it did. I'd been working in the field for about 5 years, and I'd had a few, isolated, well-received but harmless ideas that I'd published, and so I was known by the community. But then about 5 years in, I had this kind of eureka moment. This was in the year 2000, that was all about damage repair, and the realization that damage repair could be a lot easier than slowing down the body's creation of that damage. And, that was, a result of thinking like an engineer, thinking from, coming in from an engineering discipline. It took me a long time, several years, to really get my colleagues in the aging community to even understand that what I was saying was scientific, let alone to understand that it was sensible. But that did happen eventually, and so now the whole concept is much more mainstream, and I'm by no means unique in approaching the problem in that way. Now, however, that is with regard to the research community, the PhDs, not the MDs. And as you were just saying, the MDs are a bit behind the curve. They're always bound to be behind the curve, and that's not a criticism. It's that they are correctly preoccupied with things that they can already do, and they're not going to spend much of their time thinking about things that they can't already do because they haven't come into existence yet, which is the province of the PhDs. Yeah, you're right. I don't think most MDs think in terms of damage repair yet, but they will.
So, question on that. So, I've read a lot also about the information theory of aging. Can you talk to me a little bit about do they coexist? Is there is it two really distinct schools of thought? What are your thoughts there?
Yeah, so David Sinclair has been a good friend of mine for a long time, of course. He's come up with this new phrase, the information theory of aging. I honestly don't like the phrase, to be honest. I think the whole concept of theories of aging is a bad way of describing things. But putting the terminology to one side, the general principle is that there is information in our bodies that arises as a result of essentially what we are programmed to do during development, during our first 20 years of life, and especially prenatally. And that information is encoded in what are often called decorations to the DNA in our cells. So that means things like chemical adducts that are attached to certain of the DNA bases. It also means changes to the proteins that the DNA is wrapped around, things like that. Mm-hmm. And David has concentrated specifically on the first of those two things, the changes to the DNA itself. So as I say, these are not changes to the sequence. They're changes, the kind of isolated changes, often, especially one called methylation. And so this methylation information is very, very important. It tells cells what kind of cell to be. It tells a cell to be a brain cell, not a heart cell, and so on. And it's been known for a long time that that information is lost. Back in the early 1980s, a guy named Richard Cutler came up with something that he called the disdifferentiation theory of aging. And it's basically the same idea. But David has elaborated upon it by saying something about how the loss of information occurs. And he's also talked about how the loss of information can be rectified, or at least ameliorated, which is a bit like improvement of the quality of a digital image. If you imagine a digital image that loses information, because of randomization of pixels, you can get a lot of that information back, at least at the level of the image's function, in other words, of what it looks like to you and me, by not just supplying restoring the information, but just doing some averaging, essentially taking each pixel and making it equal to the average of the pixels around it. It doesn't require a process of actually knowing which pixels have been randomized and which ones have not. And there's something called partial reprogramming that's very, very high profile in the longevity community right now. It's a research area that is receiving huge amounts of funding. And I believe that partial reprogramming works essentially in that kind of way. That yes, there is this loss of information, but there's so much redundancy in the system that you can use to essentially error correct to a very large degree. Not 100%, but enough so that there's no functional deficit. Now, and so that's the way that I prefer to say it, but it's basically saying the same thing that David is saying. Now, there are other people who look at this question, and one of those people, another great friend of mine, Peter Fedichev, is not so sure that the redundancy is sufficient. And he's very worried about the idea that this loss of information could matter a lot. And one thing that he has been highlighting over the past year or so is that mice, laboratory mice, are a particularly bad organism, bad model to study this in, because they die from other things before they exhibit problems arising from this loss of information. So he and I have frequent discussions, including in public and on camera and so on, about this kind of thing. And there are certain experiments that still need to be done to definitively show that I'm right and he's wrong. But it's going to happen.
I love that. I love that. So how does this live, right? How does an information theory of aging model live next to your damage accumulation model?
Oh, it lives absolutely comfortably next to it. I mean, because this loss of information is a type of damage. It's just that it's a type of damage which, so someone like Peter Fedichev, for example, would say that the difference between those two types of damage is that the type of damage that he's talking about, which he often calls thermodynamic damage, information damage, is damage that cannot be detected enzymatically. It's not a chemically different situation. It's just a difference in, which particular bases are methylated and which ones are not, and you can't tell that just by looking at it. Whereas the damage that I've tended to focus on is damage which just doesn't exist at all, like chemical structures that don't normally exist in the body, in a young body, and they gradually accumulate over time. Or it's not necessarily even at the level of molecules. It can be at the level of cells. You can have, for example, a depletion in the number of a particular type of stem cell. That's another kind of damage that can be detected in a very straightforward way. So that's the distinction he makes. But there's no conflict between the two theories, not at all.
Awesome. That's great. That's great. So you bring up an interesting point with methylation, and I wasn't actually even planning on asking this, but I'm curious to know what you think. There's a lot of these aging clocks, and I know that Steve Horvath has done a lot of work on that, and now this is becoming a big business, right? People are able to spend hundreds or $1,000 and check their methylation patterns. You've done so much work and research in the animal models. What are you seeing as far as, do these even make sense yet, or are we still so much on the tip of the spear that they're a little bit just more directional?
There is still some way to go to make epigenetic clocks, as they're called, methylation clocks, useful in the way that we hope they will be. What we can do already is look at the methylation state of a tissue or an individual or whatever, and derive a number for how biologically old they are. Now, this number is, of course, only accurate to a certain extent, but what it means is it's a predictor of roughly how long it's going to be before such a person starts to exhibit the health problems of late life, the chronic progressive diseases and disabilities of late life. We're fairly good at that now. What we're not yet good at, and which is really the holy grail of epigenetic clocks, is to be able to do that same thing in the context of any kind of treatment that you might get. So, of course, different people that one might train an epigenetic clock on, in other words, derive which particular methylation sites to look at, we'll be looking at people with different kind of situations, different ages, of course, but also different ethnicities, different lifestyles, maybe different medical treatments. That's all great, but it turns out that they don't always work. Sometimes a methylation clock works for some people and not for others, and essentially it says that a particular treatment or a particular lifestyle somehow breaks the clock. It somehow, is good for you in terms of postponing health problems of late life, but it doesn't reduce the epigenetic clock, or vice versa, right? And so that's a problem, because what it means is that we can't use such clocks yet as surrogate clinical endpoints for treatments that are in the process of being developed. By definition, a process that hasn't yet been developed is a treatment that hasn't been developed is one that nobody who was used to train the clock has taken, right? So, right. So this is a problem. But it's possible that we will get better at this. It just remains to be seen. What I will say, though, is that there's a new type of epigenetic clock which is just coming along and which I have fairly high hopes for. And this actually connects to what we were talking about a moment ago. The thing about all the epigenetic clocks we've had so far is that they focus on places in the genome whose methylation state changes with age in everybody, okay? And so the clock is based on, well, deviations from the clock and calculations of biological age are based on rates of change, on having a non-average, below average or above average rate of change at sites that change in everybody, okay? Now, a new way of doing this is to take sites that don't change, that stay constant, but to take multiple samples from the same person and to see how different they are, how much scatter there is in how methylated they are. And that is a direct measure of this epigenetic noise thing that we were just talking about, this loss of information. There's good reason to believe that that's a better measure, a more general measure, and a more robust measure in the context of treatments than the epigenetic clocks we have today. But, as I say, it's very, very early days, so we absolutely can't say that definitively yet. It's just my gut feeling.
And just on that, I have a question. If you're taking multiple samples from the same subject, what's the time frame that you're doing that over?
The idea is that you would take the multiple samples all at the same time.
All at the same time.
Because the idea is you want the person to be in the same state for all the samples. It's just that your samples, when I say sample, actually, I'm typically talking about a single cell, right? So you'll ask, how much variation is there in a particular region that normally doesn't change at all in the methylation states of each cell. And if you see a lot of variation, that constitutes more noise than if you see very little variation.
Makes sense.
That's really fascinating. That's fascinating. So thinking about this over the long period and going back, Aubrey, I mean, where have we really gotten in the last 100 or 200 years, right, with this whole journey to aging better and extending health span and lifespan? I mean, it's typically been not a whole lot of movement overall, right?
You don't say. It's been absolutely depressing. But that is in one way a good thing, and I'll come to that in a moment. So we have made some progress, of course. What we've seen in the period, let's say, since World War II, is there has been, across the whole of the industrialized world, a steady increase in average lifespan and a steady increase in average healthy lifespan. People complain a lot and they say, oh, healthy lifespan hasn't gone up much compared to total lifespan. The gap between the two, the sick span, if you like, has gone up, has increased. But honestly, that is exaggerated. It might have increased a little bit, but only a little bit. I'm talking, of course, for people who become old enough to exhibit that in the first place. We do obviously have far more people with Alzheimer's disease now than we had before, but that's because so many more people are living long enough that they could get Alzheimer's disease. So that's not what I'm talking about. Anyway, so basically health span has increased and lifespan has increased as well as a side effect of increasing health span. But it's been pretty slow, as you say. And really, it's only come down to easy stuff, nutrition. As societies have become more prosperous, then more and more people have enough money to be able to feed themselves a good diet, and that helps, especially prenatally, it turns out. So if your mother has a good diet while you're in the womb, that stays with you throughout your life, and you live longer. So mostly it's about that. It's not really about medicine. A bit of it has been to do with medicine. Of course, medicine has improved, and we've been able to, postpone heart disease and so on a bit. But it's all rather underwhelming. So why might that be a good thing? The reason is because it's also true in the laboratory. In the laboratory, we can take mice. Mice are the species that matters the most in all of this because they've been used in the laboratory since the dawn of time. We understand how to do experiments that are reasonably reproducible, and we can ask all manner of questions that we can't ask in humans because we can't, make them breed with the people we want them to, things like that. So that's great. But the thing is, the most that we can do at the moment is about the same as we could do 100 years ago. If you take, so let's talk about numbers that matter. the numbers that matter the most are what you can do with mice that are already in middle age before you do anything at all to them, because those are, that's equivalent to people who are old enough to pay taxes. And so a typical mouse strain that would be used for this kind of thing will live about 2.5 years on average. Okay, and so we don't do anything to them until they are 1.5 years old. And then the question is, how much can you extend their healthy lifespan, and therefore, again, as a side effect, their total lifespan? And the answer is, at the moment, about 4 months. And the answer 20 years ago was about 4 months. And the answer 40 years ago was about 4 months. Before that, people didn't even do the experiments. It's pathetic. We've made no progress. So it's hardly bleeding surprising that we've made no progress in humans either, right? Not much anyway.
Yeah.
But the reason that's good news is because when we do make progress, which we eventually will, if it's big progress, if we add like a year to the healthy lifespan of mice that we don't do anything to until they're 1.5 years old, that's 3 times the effect size that we can do at the moment, right? If we can do that, every gerontologist and his dog is going to be able to come out, because they're going to be able to, they feel they have permission to be able to say, yeah, you know what, this is a fantastic breakthrough. We probably are fairly close to being able to bring aging under control in humans. And they won't get panned by their colleagues for saying things that are irresponsible and getting people's hopes up unjustifiably and so on, because it will actually be true. It'll actually be undeniable. So the question is, how do we get there? And that is what, of course, is underpinning the priorities that I'm taking in my own research at my foundation, Longevity Escape Velocity Foundation. We are focusing entirely on trying to do that. We are taking exactly what I said, mice that normally live 2.5 years, doing nothing to them until they're 1.5 years old, then throwing the kitchen sink at them, because that's what we do. We're interested in damage repair, which means we're interested in a divide and conquer approach. There's lots of different types of damage. You've got to have some impact on all of them in order to get a significant increase in lifespan. And typically we're starting with interventions that already have some effect individually, right? But we're throwing them together to try to get a bigger effect in total. And the first experiment that we've done in that area, which began early last year, is nearly over. It's not really got very far beyond the 4 months. We might get 4.5 months, so it's definitely not anything out of the park yet. But we've learned a huge amount from that experiment, and we've, of course, seen other people in other labs around the world doing stuff that also looks promising. So we are burning to start the next experiment along the same lines, but with different interventions done in slightly different ways. And the only thing that's stopping us from doing it right now is we don't have the funding. That is a real problem, because the thing is that, as I said, there is a huge amount of money coming into some areas of longevity research right now, such as partial reprogramming, but only some areas, because the money's coming in typically from investors, people who actually want to make money. They want a return. And so that means there's two problems. One problem is that a lot of the things that we would want to do to mice in order to do these experiments are just not patentable, or they're off patent. Like metformin or rapamycin or something like that. These things have been off patent since before I was born. And so no one's going to make any money out of them. And the second problem is that even for things that are patentable or are patented, different interventions are patented by different people. And so there's a huge amount of inertia there trying to bring that together. It's pretty difficult to create new IP from combining things that already work. The IP is not as strong as all that. So it basically relies on me because it relies on philanthropy. And I run the only organization in the world that gets significant input from philanthropy in the longevity world. Anyone who's listening and who wants to help, get in touch.
Absolutely. So I've been following your latest study pretty closely,
okay.
And I know that you're just tying that up. What is the most exciting thing? I mean, given the fact that you haven't seen huge gains on there, which may or may not be expected, what is the most exciting thing that you've learned so far personally from that experiment?
Tricky question to answer, because we've learned quite a lot of things. One thing that we saw in this experiment was that there was a big difference between male mice and female mice, and we're definitely going to want to know whether that is reproducible. Male and female mice in this particular strain, C57 Black 6, are a little unusual in the difference between them. Namely, the males live longer than the females, which is, of course, pretty unusual in any species. And in our experiments, we've seen quite a lot of differences in the trajectories. But the bottom line is that there is additivity. Certainly in females, you can look at the curves; they're pretty. The message is pretty clean. That you get a certain amount of improvement from each of the things individually, and you get the best performance from putting all four of the things we're doing together. In males, you also get the best performance from all four, but interestingly, in females, the worst performance is, as you would expect, the controls that get none of the things, and in males, actually, there are some treatment groups that are getting some of the things, and they're doing worse than the ones that are getting nothing, and that changes with age as well. Some of them were doing really badly early on, and they caught up. Some of them were doing fine early on, and they fell off a cliff. So there's lots and lots to interpret there.
Oh, that's interesting. So, how does this all play? If we talk about the longevity escape velocity, let's turn the corner for a minute, because I don't know that a lot of our listeners are super familiar with what even that means, right? So I am super passionate about making sure I make it to the point where we have escape velocity, Audrey. So I am making sure that I am doing as many things as I can to be as healthy as I can for as long as possible. But can you explain how that really works and what that means in context?
Sure, yes. So normally we think of short-lived species, laboratory species like mice, as inherently easier to manipulate than humans. We see, for example, that only a small proportion of the drugs that succeed and get through the preclinical phase, because they actually achieve what they're supposed to achieve in mice, then follow through and also succeed in humans. But there's one exception to that, which is this thing, longevity escape velocity. So this all comes back to the fact that we're doing damage repair, that we're taking organisms that are already in middle age, in other words, they've already accumulated a bunch of molecular and cellular damage as a side effect of being alive, and we're removing that damage. Now, the thing is that there's lots and lots and lots of different types of damage. So we have to do lots and lots of treatments together. Of course, there are some kind of knock-on effects. You remove one kind of damage, then somehow the body gets better at removing other types on its own, things like that. But basically, you've still got to do a lot of different things at the same time. What's going to happen initially is we're going to be able to eliminate some kinds of damage and not others. And if we can do that, reasonably well, get a reasonably comprehensive portfolio of interventions, then we'll get an increase in health span. And as I say, a side effect being increase in lifespan. But it won't be indefinite, because there will be some kinds of damage that the portfolio doesn't work on. And those kinds of damage will continue to accumulate, and eventually, on their own, however well we remove let's call it the easy damage, we will still see the individual getting sick and dying as a result. So that's a problem. But it's less of a problem for long-lived species like humans than it is for short-lived species like mice. And here's why. If you take a mouse that's got an average lifespan of 2.5 years, and you treat it at 1.5 years old, let's say you can make it biologically 1 year old. That sounds good, right? But then it'll be biologically 1.5 again, only 6 months later. Mm-hmm. And in those 6 months, we won't have learned all that much. I mean, the whole world will not have learnt much about how to do better, how to repair some of the difficult damage, and thereby rejuvenate the mice. We will have to just carry on giving them the same treatments, and that won't work, because the difficult damage will still be accumulating, and the mice will just get sick and die 6 months later than they otherwise would. All right? But if you do it for humans, it's a different matter entirely, because you take someone who's 60 and you rejuvenate them back to being 40 biologically, right? Then you've got 20 years before they get back to being the same biological age as they were when you treated them. So the problem is the same, but the time that you've had, the time that we, the researchers, have had to improve the comprehensiveness of the portfolio is 30 times longer, 40 times longer. So we're basically certain to have been able to do enough that we can rejuvenate the same people who are now 80 but biologically 60 for the second time. So they won't be biologically 60 for the third time until they are, chronologically 110 or whatever. And that's the goal. That's what I've called longevity escape velocity, the minimum rate at which scientists need to improve the comprehensiveness of these damage repair therapies so as to so that people who are getting the state-of-the-art therapies at any point will stay one step ahead of the problem and will never actually start to have enough damage so that they exhibit any health problems. The threshold, however, is we won't get to that point until we get those first 20 years. If we only get 5 years, that's not enough time for the scientists to improve the therapies enough. The good news is things are moving faster. 20 years ago, when I invented the concept of longevity escape velocity, I said that it wouldn't kick in until we had the first 30 years of increase, and now I'm saying only 20. The reason for that is because basically things are moving faster. There's more scientists working in this area, so we can be a little more optimistic.
So
That's
then,
so great.
What is the possibility of using these things on humans within your research? How close are you in that area?
So this comes back again to the fact that some things are easier than others to repair. Mm-hmm. At my previous organization, Sense Research Foundation, I very much focused on that hierarchy of difficulty. And the work that we were doing was to develop ways to repair the most difficult types of damage. Because what I could see happening was that the easy types of damage were already being pursued by other people in labs around the world, whether in private sector or in academia, and things were going all right. So we wouldn't be actually contributing much if we worked on them as well. Whereas the difficult ones were being neglected because everyone who works either in academia or in the private sector, they are enormously constrained by short-termism. People who want to make money, investors, they want to make it tomorrow, and similarly, academics, their priority is to get their next grant application funded, which requires them to get papers in top journals, which requires them to get positive results. So again, it's all the low-hanging fruit. Anyway, so that was what I did before. But now that we have reached the point where it's possible to combine things, because enough things are working individually, at least a little bit, that's why at LEV Foundation I have this new priority. But of course, the things that I'm combining are the low-hanging fruit, the things that I never worked on previously. The other ones are just not ready they're not sufficiently ready for prime time to be includable.
Do you feel like some of the things like Matt Kaberlin's doing with the dog aging project and things like that, where they're sort of trying to pull out of the mice studies into larger mammals? I mean, is that something that you think is going to yield some positive knowledge?
Oh, absolutely. I'm a big fan of Matt, very much so. I mean, I was as appalled as everybody was when about a year ago the NIH actually defunded the dog aging project. They actually said we're not going to get it.
Yeah.
I mean, everyone was completely speechless. He's just about managed to keep it going by scraping together money from elsewhere. But yeah, it's an absolute scandal. Anyway, though, yes, the utility of all this, absolutely. We've got a couple of things that we can get from studies like that you can't get so easily from laboratory studies of mice. The first is the dogs are not in the laboratory, they're in the community. And so it's very much more heterogeneous population, and of course heterogeneous not only genetically, but also in terms of their environment, their exposure to infections, things like that. So that's helpful. Another helpful thing is that they are, they're intermediate in lifespan between mice and humans. So they're closer to us in that regard. There are downsides, though. I mean, fact is that the heterogeneity I just mentioned does translate into limitations on reproducibility of experiments. You may get results that you don't get next time. And of course that's true in any experiment, but it's perhaps more true in something which is being done in the community. Nevertheless, we definitely need those experiments just as much as we need experiments on mice. At the moment, one thing I have to mention, though, is that there's not enough work on dogs, and the work that is being done, because it's being done in the private sector or in academia, is subject to the short-termism I mentioned a moment ago. There is absolutely no work being done on dogs that is analogous to the work that we're doing on mice, with combinations of things being done at the same time.
Yeah, so you mentioned the kitchen sink approach, which of course, makes me want to bring up Brian Johnson, who I think you are friendly with, right? So Brian's theory is all about the kitchen sink approach, right, and throwing as much stuff on and testing. How has that kind of human data really moved forward for you? I mean, are you getting that kind of stuff from Brian? Is that influencing you at all?
So I'm a big fan of Brian as well, but I want to make sure to explain in which ways I think Brian is doing admirable things and in which ways I think he's making a few mistakes. He's doing admirable things in being so upfront with the world, and going out and telling the world all about what he's doing and why. A lot of the things that come under the why category are, things that really turn other people off. They say, because he likes being told what to do by a computer, basically. That's the way he says it. That's very alien to a lot of people. But the fact is he's completely shameless about it, and that's great. He's totally leading by example in terms of not being, driven by what's normal. So that's very important. In terms of what he's doing, well, certainly the big thing that he has, emphasized very strongly as vital, and he's completely right, is measurement. That the more you know about the state of your body, the more likely you are to get things right in terms of interventions. And in his case, something that came out of that's very, very important to him is sleep patterns. But this comes down to something that I always have to emphasize when we're talking about things that can be done already, which is that different people are so different. I, for example, I can sleep on planes. I can sleep whenever I want, whenever I'm tired. I don't get jet lag at all. So, so sleep is not a priority for me. I have to get enough, but I don't have any problem getting enough. Whereas someone like Brian, he really, there was a long period of time when he simply would never take a flight that crossed more than 2 time zones, just in order not to disrupt his sleep patterns. This is something that, he found out by carefully looking at himself. And anyone can do that. You don't have to do what he does and spend $2 million a year on yourself. You just pay attention to what works. One thing that I often bring up these days is gluten. Gluten intolerance is something that's a big deal these days. Everyone knows about it. Everyone hears about it. Whereas 10, 20 years ago, that wasn't the case. But nobody does anything about it. It actually makes some kind of sense for people to actually give up everything with gluten in it for a week and just see whether they feel any different. Because people discover that they're gluten intolerant when they're like 50. And they've lived with it for a long time, right, without even knowing it, right? Those kinds of things. Just find out what works for you. I do want to emphasize, though, that this is probably not going to be very much the case when it comes to damage repair. When the things I work on are ready for prime time, the thing is that we all accumulate the same kinds of damage, the exact same types. The only difference between different people is that they accumulate different types of damage at slightly different rates. And that doesn't change the efficacy of treatments that remove the damage.
So do you feel like some of these influencers or folks like Brian are potentially causing a little more friction around that sensationalism and where we need to go as a society, right, and our feeling around this longevity escape velocity?
Messaging, yeah, messaging in this whole field is an absolute nightmare. When I started out 25 years ago or more, I started doing public speaking like 20 years ago or more, one thing that helped me a lot was that I look the way I do, simply because that my priority back then had to be to distance myself from the people in suits and ties who were trying to make money out of snake oil, out of things that didn't work.
Yeah.
Right?
Yeah.
This thing called the anti-aging industry. And so that worked okay. But today we've got this whole spectrum. We've got people who academics who won't talk to the media at all because they think they're going to be misrepresented. We've got academics who do talk to the media, but they're very, very careful about what they say because they have to worry about their next grant application. We've got people like me who are in the non-profit sector, but who have been able to do it in a way that's outside of the system, so I can tell it like it is. You've got people in the private sector who are mainly focused on giving returns to their investors, and so they have to say things that are perhaps not the whole truth. And then you've got influencers who make money out of being influencers, people like Peter Attia, who, take a particular position just because one has to have a particular position in order to get an audience of that kind, and who are pretty unreasonable in some ways as a result. And then, of course, you've got the bona fide snake oil salesman. So, some people are doing actual damage. Nearly everybody is doing good in terms of raising awareness, but different audiences resonate with different people. Like Liz Parrish is a great example. Great friend of mine came into the field maybe 10 years ago, acquired a big platform by virtue of doing gene therapy on herself, and has used it fantastically because she's smart enough to have been able quickly to learn enough science to be able to not make a fool of herself. But at the same time, the way she says things is completely different from the way that I say things. She's a heartstring puller, and I'm a geek. So that's been enormously beneficial. That's what we need. We need variety, we need diversity of messaging, and we have that now. And that does have its downsides, but overall it's a net positive, a big net positive.
Yeah, and it's such a beautiful accumulation of all of this that we're working on together. Now, I want to bring this back to your foundation in that if you had, I kind of like to, pull on the heartstrings a little bit here and dream big, but if you had, unlimited funding, how much would that be? And then what could you do with that? And what could the possible outcomes be? Because that's what's really exciting. And then give us, again, the name of your foundation. So if anybody out there has that kind of funding and can create these possibilities, let's do it.
So, the name of my foundation is LEV Foundation. LEV stands for Longevity Escape Velocity. And the website is levf.org. And we have a nice friendly donate button at the top of the page. And if you want to give substantial money, then obviously my email address is there too. How much money would we need? Well, there are two answers to that question. There's how much money would I need to do the work that I'm best placed to do, and that how much would the entire longevity community need to do everything that needs to be done. The answer to the second question, honestly, you could put it in the hundreds of billions perfectly easily, because you would need a huge number of clinical trials, training of medical personnel, building of infrastructure, all that kind of stuff. But the work that I do, we're talking much smaller numbers, because I work on the early stage stuff in the laboratory rather than in the clinic. And that work is just inherently less expensive. But it's still not nothing. So the experiment that we're just bringing to an end now, that we started in early 2023, cost about $3.5 million. And there are still bits of that need to be done. Maybe there's another $1 million to be spent. Every experiment of that kind is going to cost that kind of amount because it needs 1,000 mice, basically, maybe a couple of thousand, depending on how we're doing it. And, there's no way to reduce those costs. Not much anyway. We're obviously always looking for ways to reduce them as much as we can. So, how many experiments of that sort do I think need to be done? I think I could certainly do a dozen of those experiments tomorrow if I had, $100 million. And the question then is, what other experiments would I want to do? There are a few. There are things that still need to be done better in the category of getting further forward on the really difficult types of damage, the kind of things I worked on in my previous organization. But I probably couldn't spend more than about $500 million right now. Maybe not even more than a couple of $100 million. you know, which is pocket change to quite a few people I know. And that is depressing.
Mm-hmm.
Yeah, it's amazing what the focus points are in, among those with that kind of money. And I mean, I know Bezos has put in a bunch of cash, and the Saudis have put a bunch of, I mean, a couple billion, I think. So I know there's a lot of money floating around there, but I think you're right. I mean, the vast majority of that focus is really centered around how are we getting an ROI on this pretty quickly.
Yeah.
So you mentioned earlier that you had done work around AI. I mean, without going too much into down that path, I mean, how is that helping you now, right? With all of these learning modules now, I mean, is that really giving you a really good accelerator, an exponential way that you can move forward with your experimentation?
It's not helping me personally because my work back then, we're talking the 1980s and 1980s. So AI research was a completely different animal back then than what it is now. This was before, the discovery that neural nets could actually do interesting things. So I was, developing programs that would identify mathematical proofs of things. It was all symbolic, formal system stuff. So, it helped me early on, as I said, thinking like an engineer, but not really now. But if we talk about how AI as we know it today is helping the field, then it's astronomical, it's enormous. It's no accident that, it wasn't only Geoffrey Hinton who got the Nobel Prize, it was also Demis Hassabis, because, AlphaFold is at least as big a thing in biomedical research generally as the sequencing of the human genome was 20 years ago. Not that it necessarily allows things to be done that could not be done before, but that it allows a huge number of things to be done much, much faster than they could be done before. And that means more things are going to be done, right? Drug discovery is going to be much more efficient, and so on. So that's all wonderful. And, of course, Demis is leading an effort, not just restricted to AlphaFold, of course, that is very much keeping its eye on the humanitarian benefit of everything, and he's kind of being allowed to do that, despite the fact that nominally he works for Larry and Sergey. So yeah, I mean, that's critical, and of course there are plenty of other things that are going on in the same vein, things that are going to be relevant to all biomedical research, but are absolutely going to be relevant to aging. And there are some things that are a bit more specific to aging. In general, yeah, AI is changing the world very fast, and changing the biomedical research world in particular very fast.
So for those of our audience who are thinking, Aubrey, that they've heard all this, they're new to learning about what you've been doing. They know what we've been talking about as far as Janae and I are democratizing a lot of this data, right, and trying to get a lot of this stuff out in a way that everyday folks understand. As they're thinking about biding that time over the next 5, 10, 15 years, let's say, and there are things that are on the market today, like even getting preventative stem cells versus IV and things of that nature. Are there things that you might say, hey, listen, if money was no object, right, and there were potentially some things that folks could participate in today and over the next 10 years to keep them at that place, to accumulate the least amount of damage, right? Mm-hmm. What types of things might you suggest that they consider?
All right, so first of all, I remind everybody that I am a PhD and not an MD, and therefore I am not legally allowed to make recommendations, let alone, and I don't really have the expertise anyway. However, what I can say is this. First of all, live the way your mother told you to. Don't artificially shorten your life by, smoking or getting seriously overweight or eating a bad diet or anything like that. Honestly, if you're doing that, then you're doing 90% compared to most people of what you can do in terms of the overall impact on how long you will stay healthy and avoid the health problems of late life. In terms of other things that one can do today, the difficulty that one has is that different things work for different people. I mentioned this earlier in terms of sleep with regard to Brian Johnson and so on, and therefore you have to know what works for you. a lot of that you can do by just paying attention to your own body, just by just seeing what works. But a lot of it can be augmented by getting measurements, just going in and getting a comprehensive blood test, to figure out what bits of your metabolism seem to be, a little bit out of whack. Getting your genome sequenced, it costs $1,000 these days. It's not a lot of money, and that'll tell you, what susceptibilities you have, to the extent that that correlates with the susceptibilities that your blood test gives you. Then that's stronger information. One can get information about what supplements to take. So here's an example from myself. So I happen to have a polymorphism in a gene called mTHFR, which, I don't have to go into the details of what it does, but one of the things it does is it makes use of vitamin B12. There are various forms of vitamin B12, and there's a particular form that's useful for various things downstream. And you need that gene to be working well in order to make that particular form. Turns out that the supplements that one gets are of various different forms, and generally it's not that form, right? Now, there is some interconversion in the body, as I say, but that interconversion is reduced if you have this polymorphism that I've got. So that means that I shouldn't just be taking vitamin B12 because someone measured my blood and said, oh, the vitamin B12 is low. I should actually be taking a particular form, what's called methylated B12. This is a different use of methylation than what we were talking about earlier. And that will have more of an effect on my metabolism, more benefit, than if I take other types of B12. These are the subtle details that one can only find out by, but you only need to do it once. I mean, of course, you only need to do your genome once because it doesn't change. It helps to get a blood test, when you can, right? I get it every year. But once is a lot better than not at all, right? So that's another thing. But then that brings me to the third thing, which is absolutely critical. If the goal here is to postpone the health problems of late life, to live as long as you can without exhibiting those problems, then there are two ways to do that. One is to postpone the age at which you will get those things with the things that you can do today, whether it's lifestyle or supplements or whatever. Another one is completely different. It is work to hasten the arrival of, and your access to, treatments that don't yet exist, right? Now, there are lots of ways you might want to be able to do that. If you're wealthy, you can fund my research. If you do a podcast, you can interview me, which you seem to be doing right now, and get the word out and improve the world's understanding of these things. If you're a biologist, you can choose the most impactful areas of biology to go into, to spend your career on. If you have access to the corridors of power anywhere, then you can alter modernize regulatory regimes so that access to new treatments is provided faster. There's a lot of things that people can do. And of course, absolutely everybody, even if you're not in any of those categories, you can talk to your friends and your colleagues and your family and so on. People often say, oh dear, I can't help because I've got no money. And I always say, well, that doesn't work, does it? Because the poorer you are, the more people you know who are wealthier than you. And and that means you can do things by advocacy that you can't do with your checkbook.
I love that.
Yeah, that's great.
I think that's a great place to put a bow in it, Aubrey. You are absolutely delightful. Thank you so much for joining us and shedding light on this. I've been following your work for quite some time, so this is a thrill for me personally, just in a narcissistic way. This has been a lot of fun. Janae, is there anything else that you wanted to mention?
Well, I am just thrilled. Yeah,
Thank
go
you so
ahead.
much. Yeah, I think I've pretty much covered what I wanted to cover. I cover different things in different podcasts, but this will do fine. And certainly, I hope I've been able to get the message across that the work that we're doing at LEV Foundation is absolute critical path to helping people, saving lives, to keeping people healthy, to alleviating suffering, improving people's quality of life as well as quantity.
Absolutely. And we're going to be including links to everything in the podcast description and below. So as you guys are, watching this, just look below. We'll have a link. You can check out what they're doing at the LEV Foundation, and you can donate. And donating to them is donating on behalf of us and our mission here, which is really all the things that Aubrey just said. This is super. This is fantastic. So, Aubrey, thank you so much on behalf of me and Janae. Hope you have a great rest of your day. And if anybody has any questions, feel free to leave some comments below, and we'll get you in contact.
Fantastic. Thanks so much for having me.
Thank you.
Thanks for joining us on another episode of the Becoming Young podcast. Quick reminder that this is not medical advice and no doctor-patient relationship is formed. If you're facing a healthcare concern, please consult your primary healthcare provider. We can't wait to see you next time, where we're going to talk about more ways to keep you looking and feeling young. Click through to watch some more videos.